Hey everyone, got a test coming up? Or maybe you just need a super quick refresher on what an atom is all about. Well, you are in exactly the right place. This is your ultimate 5-minute revision on atomic structure. Let's do this. First things first, if you find this whole topic a little bit confusing, don't worry. You're definitely not the only one. Protons, neutrons, electrons, yeah, it can feel like a lot to keep track of, but we're about to make it all make sense.
So, here's our mission. We're just going to tackle the biggest, most important questions about the atom, one by one. And by the end of this, you'll have all the core ideas totally locked in. Ready?
Okay, question one, let's get right to it. What is an atom even made of? Turns out it's got 3 key building blocks.
This table lays it all out perfectly. Right in the center, in that dense core called the nucleus, we find the heavy guys, the positive protons and the neutrons. Then, whizzing around the outside in these paths called shells are the tiny negative electrons. And just look at the electron's mass. It's practically nothing compared to the other two. So now we know what's inside. But how do we know how many of each particle a certain atom has? Well, it's all about cracking the code that you see on the periodic table.
There are 2 numbers you absolutely have to know. First is the proton number. Think of this as the element's unique ID card. Every single carbon atom in the universe has 6 protons, no exceptions. Then you've got the nucleon number, which is just the total count of everything heavy in the nucleus. So that's your protons and neutrons added together.
And this is how we write it all down, using something called nuclide notation. So, if we look at our carbon-12 example, that top number, 12, is the nucleon number, and the bottom number, 6, is the proton number. See? It's a pretty simple code once you know it.
So if the top number is protons plus neutrons, and the bottom number is just the protons, how do we find the number of neutrons? It's easy. You just subtract the bottom number from the top one. For our carbon atom, that's just 12 minus 6, which gives us 6 neutrons. Simple as that.
All right, now this is where things start to get really interesting. Atoms aren't always neutral. What happens when they start messing around with their electrons? Well, they become an ion. An ion is simply an atom that has an overall electrical charge. And here is the #1 most important rule you have to remember. An atom becomes an ion only by gaining or losing electrons. That's it. The number of protons in the nucleus is locked in. It never, ever changes. So here's how that works. In a normal, neutral atom, the number of positive protons is perfectly balanced by the number of negative electrons. The overall charge is 0. But in an ion, that balance is totally broken. The protons and electrons are not equal anymore, and that's what gives it an overall positive or negative charge. And of course, we've got names for these. If an atom loses some of its negative electrons, it has more positive protons left over, right? So it becomes a positive ion, called a cation. Here's a little trick. Think of the T in cation as a little plus sign. And if it gains extra negative electrons, it becomes a negative ion, called an anion. On to our next big question. Can you have different versions of the same element? Oh, absolutely. The best way to think about them is like atomic cousins. They're all part of the same family, but they aren't quite identical. And these cousins are called isotopes. Now the key phrase here is same element. And what's the one thing that defines an element? The number of protons. So isotopes have to have the same number of protons. The only thing that's different about them is how many neutrons they have packed into their nucleus. Hydrogen is the perfect example to look at. See, all 3 of these are hydrogen atoms because every single one has exactly 1 proton. But look at the neutrons. Regular hydrogen has 0 neutrons. Its cousin deuterium has 1 neutron, and the other cousin tritium has 2. Same family, just a little different on the inside. So what does this actually mean for how they behave? Well, because they have the same number of protons, they also have the same number of electrons. And since electrons are what control chemical reactions, isotopes have almost identical chemical properties. But because they have different numbers of neutrons, they have different masses, and that changes their physical properties, like how heavy they are.
Okay, so we've covered the particles, how to count them, what ions are, and what isotopes are. But what's the point? I mean, why do atoms even bother gaining or losing electrons in the first place?
It all comes down to these guys right here, the valence electrons. These are the electrons in the very outermost shell of an atom. Think of them as being on the front lines. They're the ones that do all the interacting, and they determine an atom's entire chemical personality.
And for most atoms, this is the magic number, 8. Having 8 electrons in that outer valence shell is like the ultimate goal. It's a state of complete stability. It's what all the super chill, unreactive noble gases have.
And this, right here, this is the driving force behind pretty much all of chemistry. Atoms are constantly trying to get that stable, full outer shell. They will do whatever it takes, gain electrons, lose electrons, or share electrons, just to get there. That is why ions form, and that is why chemical reactions happen in the first place.
So, let me leave you with a final little challenge to see if it all clicked. Imagine an atom has 7 electrons in its outer shell. What do you think is the easier path to stability? Gaining just one more to get to that magic number 8? Or going through all the trouble of losing all 7? Think about it, because if you can answer that, you're on your way to understanding all of chemistry. Thanks for tuning in.